Good afternoon, ladies and gentlemen. Welcome to my presentation. My name is Matthias Brockmann, and it's a very great pleasure for me to present to you today our ideas of the Internet of Production at RWTH Aachen University. As you can see, I'm responsible for something which is called the Cluster of Excellence, and I would just like to give you a short introduction of what that is and what it means for the German science landscape. As you can see on the slide in green, there are universities in Germany which are stated to be elite universities. And the rules of the games work like this, that you need to have at least 2 so-called clusters of excellence. And after that, you can apply to be an elite university. So it's kind of the first league of the Bundesliga in football in Germany, clearly with a focus that in Germany we have decided to have universities with a clear profile of the universities where they are good at. And in Aachen, that is the case for 2.5 clusters, whereas one is a so-called fuel science center and the other one is the Internet of Production, which clearly deals with the digitalization in production, which I will try to inform you about today a little bit more. What you can see also on that slide, and I think that is the most interesting thing for us as researchers in such kind of a project, is the time frame of this objective. You can see that now we have a funding for almost 14 years, so 2 times 7 years, and this group is coming out of a further funding of 12 years. So it's kind of very long-term research, which gives us some very good benefits, which I was trying to show you on this slide. You see that we have over 35 institutions and 200 scientists involved at the location of Aachen. And of course, you maybe also know about the world of science at universities, that in normal times you have project funding for 2 or 3 years, which of course is not long-term or sustainable. And this kind of a project gives us the opportunity to really go into a long-term interdisciplinary collaboration between scientists. So I tend to say sometimes that this cluster of excellence is something like a National Center for Production, which due to the German science system and the boundary conditions is not called like this, but in fact it's something that could be said like this. And you see here that we are the only cluster in the area of production engineering throughout Germany that you saw before. So just one short comment of how is it working in location like Aachen. You could compare it a little bit to the national soccer team of Germany, if you want so. So we have our big clubs that are our institutes and our professors, and we take out, let's say, the players that we need on the certain positions that we need in order to follow our research roadmap for this 14 years. That means also that the staff can change from year to year, and that we can bring new expertise into our cluster if we need them. And that is something which, in my opinion, is a very big benefit within this cluster. And maybe that's also something which I can say from my daily work, that really we have brought it now to some kind of real interdisciplinary. And what is basically new, if you want so, is a collaboration with our computer scientists that are depicted here on the lower right side. I didn't put names, but you see some faces of people who have coined the German world of production in science. You can see Professor Schuh, who is a leading part of the Akatech. You can see Professor Stich, who is one of the inventors of the maturity index Industry 4.0, which is coming from Aachen. You can see Professor Brecher, who is a leading person in the WGP, which is the German Society of Production Engineers. Our structure is similar to that of a big institute or a company. We have a management board that is managing all the activities, and we have research areas called CRDs, cluster research domains, and beyond that there are work streams which are similar to groups. And for me, what is important to mention is that the smallest unit of these clusters are 5 or 6 professors who are working in collaboration. What you can also see on the upper left part of the slide is that we also have advisory boards, which is on the one hand a scientific advisory board, but also an industrial advisory board, and I show the members to you here. It's like this, that these board come together every year. We have sometimes very high-ranked members in this board coming from the executive level of these companies, and we have people from the areas of digitalization in this board. And so once a year we come together and get the advice of this group of companies, and it helps us a lot in order to not do science only for the sake of science, but bringing that also into transfer into the society and into the industry. And that is one major part, and it's also why I'm so happy that I can present to you today. I would just like to give you a small insight. I will not go too deep, but a little bit about the science and the topics that we are looking at in this cluster. And now it was important for me to a little bit describe the organization of our group, because you can see that it's more or less like a roadmap, and you can see that I put it on slide number 1, that in a sense what we're doing here is like a funded roadmap, if you want so, of the RWTH Aachen University, combining many different disciplines. And of course, Internet of Production in this sense is a metaphor for the socio-technical connection of humans, of models, and of machines, of data in the production. I don't know if somebody of you had the chance to be in Aachen. I think that universities are a little bit different in Germany, so you can see it on this slide. We have integrated over 30 laboratories, but if you have a look inside of those laboratories, well, it's more like a small and medium enterprise in terms of up-to-date production machines. We have all kind of different production technologies, from casting, grinding, additive, turning, milling, and so on. We have all that inside of Aachen in our institutes. And that always used to be our big strength in the landscape of Germany, that we have this very high level of specialization in production technology. But on the other hand, this high level of specialization, it can also be a disadvantage if we talk about speed of innovation, and if we talk about exchange of information. So in a way, and I think that is what also German Science Foundation say to us, is that we are like a small model world of the economy, of industries in Germany or other countries. And that's why it's so interesting, our collaboration, because we're facing basically the same problems and challenges that people in reality have. So just to give you an idea of that, the first year, so we're going since 2019, which you saw on the slide. The first thing that we do was to build up a data lake in Aachen. We're doing this with an open source provider. And we have a brownfield like it is in reality. That means some of the laboratories, they have computer numerical control, of course, and they have direct connection of their cyber physical systems to the data lake, whereas other institutes, they need to bring the sensors on the machine in order to get the data to the data lake. And that's exactly the same that we're facing. But in fact, now we are able that all of this very heterogeneous laboratories can bring data into our data lake of Aachen. And if I need to describe our vision or what we are trying to do with this data, very easy, I usually use Google search, because it's maybe the most easiest way to understand. So what we're going to want to do with all that data in the lake is, on the one hand, we want to bring it together in a way that is semantically adequate. There's a city called Aach in German, which you can see, which is syntactically very close, because it's also the letter AACH, but we mean something totally different. So that's clear. We want to put semantics on the data, which is the engineering knowledge in our world. We need context-aware data. That means that people who have searched for the city of Aachen, maybe they want to look at the sites that you can visit in Aachen. And of course, that is also something which is very important in terms of the data that we can get from production, where they are connected to, right? I will go to that a little bit later too. We need data on the right level of aggregation, on the right level of granularity. Also, a small example here about a small excerpt from Wikipedia that you can see with a fact sheet and very short description of what is going on. And what you also know about in Google is that you can have some kind of real-time information. Well, it's not real-time information in the sense that you can fly an airplane with this weather information, but you can decide if you need to take an umbrella or not, right? And that's some kind of, that's a very good metaphor of what we're trying to do in production technology. Real time also is dependent on the domain that we are looking at. In a machine tool, real time, it means in milliseconds. In the design, it could be even one day, and it would be real time, right? And that's, I think, something that is very important also for our world of production. When we talk about data from the sensors and from the cyber physical systems, we're not so much after what I was saying, that we need to put new sensors on the machine, basically, but we need to understand which data or which sensors are already available and how can we make them accessible. And that's on the one hand, of course, semantics, what I was saying, or it means putting the right metadata on the data, of course. I think that is something, if you look in our laboratories and the engineer is doing an experiment and he's writing a sheet about experimental plan, there are the right metadata on this plan. So that means if we are having a test on a production machine, let it be a turning action, then of course the gravity of the moon has an impact on that physically. But it will be not interesting. Maybe it will be more interesting to measure the temperature in the shop floor. And that's what the engineer or what the expert is doing. He or she know exactly what is the right metadata that we need to put in. That's clearly the challenge number one that we are now doing. Second point is in our university, but also in your companies, there is a lot of knowledge available. And we in engineering, I think we have two sources of knowledge. On the one hand, that are all the standards that we have, that Germany, they like a lot of standardization, but the standardization papers are on paper. So we have no way to access that in some way digital, like you see on the slide of Google. That is the so-called knowledge graph of Google, which gives the opportunity to connect knowledge that is there before in terms of a structure and a common vocabulary, but we don't have that yet. So that's one thing that we're working on. And if you look at this university, clearly we have a lot of doctoral theses and a lot of papers. And here that is the same. If you look normally on PowerPoint slide number one of all our PhD students, they have a lot of expertise in order just to show where their PhD thesis is located at the landscape of science. Alone, if you can say and show where is your point of science in this very high specialized world, you have already bring knowledge to the system, right? And that's what we're doing here. We're having a common standard of ontologies and taxonomies and knowledge graphs in our cluster, and we're seeking for standardized way of putting metadata to the data itself. What we would like to do with the data is something that we call in our concept the digital shadow. So you might also know the term digital twin. Let me say you with a very easy metaphor, and I'm coming back to soccer, sorry, because Germany like it, but I know Brazil people also like football, of course. Maybe you are aware of the game FIFA Soccer. I think you are on PlayStation or Xbox. So if you want, so that is a simulation. It is a model of football. And now there were two streams that we could observe in the past, that the one stream for going into the future is to make that simulation better and better and better, in a way that you can see the faces of the people in the stadium, or you can see the grass and so on and so on. But the second, maybe more interesting development of the simulation was the integration of the live performance of the players into the game, which means that if a player is playing bad in reality, he will also play bad in the game because it's changed the stats live. And that is in a very easy metaphor, of course, what is our opinion of the digital shadow? That means that we need to bring together live data from all the different domains. That is the development of products, that is the manufacturing and production, and that is of course the usage of a product, together with the simulation models. And in this sense, the digital twin on this picture can be found on the lower left side. It's the source, right? It's a source of data which, similar like the sun, can go onto an object and give a shadow. Similar to that, we need to bring parts of the digital twin together with real data in order to find correlations which are useful for production technology. And you can see that here with a very short example, one use case that we're doing, that if, for example, for a milling machine, you can bring data from the location, from the NC data, from the location of the tool, together with data from sensors inside the machines, which are already here, which can be correlated to the force, and bring that together with a simulation of the quality of the things that you're producing. And I think that is the real interesting thing, that if you look at this, let me say, structure with all the circles that you can see here, that's clear, that's a data model. And the interesting thing is the knots between the data model, because within inside these knots, there's hidden the engineering laws, and we do not have so much mass conservation, energy conservation, and so on and so on. All of that is hidden inside of this data model implicitly, and these laws will not change, right? And that's the interesting thing, in my opinion. And that is one kind of example that I was also showing before. It is looking like a normal simulation that you are doing, but in fact, it's a simulation which is connecting a lot of different models from the machine. How is the machine behavior? How is the tool behavior? What is the component doing? And it's predicting if a part goes good or not good within the production. The parts which are red are not good, the green parts are good. But what is done here, and that's the essential point in my opinion, is that the validation is done in every time step according to live data from the machine. That means what normally is done in science is that you build a model, you build this wonderful, colorful picture. Afterwards, you go to the machine, you make your experiments, and you will compare these two pictures and say, oh, that was good, but no, here we have some kind of a problem, and we will go back into simulation and change the parameters and do that as long as it fits to reality. And that is done in this case in every time step. So that's the first benefit of the digital shadow. But the interesting thing now, when I'm coming back to which kind of data we want to show, it's exactly this data. So it's like refined data with physics that we will not put in our data lake, all data which is produced from the machine. But we want to put in this lake like data which is refined with physical information, and which of course have some kind of, like an ISBN number in books, they can show where is the source data itself. But the interesting thing is data which is prepared like this. What we can do with this data is, of course, on the one hand, different kind of business models. We are a fundamental research project, so we are not so much interested in business model itself. But what you can do, of course, with this is some kind of systematic learning throughout different machines, like you can see here from this Google Kindergarten, which you all might know, in the sense that if this robot now is able to grab this blue part, all other robots on the world are connected by internet, and they also know how to grab this blue part. That is a very easy, let me say, similarity where we can see already that exchange of data is useful. But now, if I'm coming back to this picture of the digital shadow, if we are able to, bring that data back to physics, then of course also a car could learn from a robot. If we talk about the bearing or other things where the components itself only see force, they see temperature, they see vibration, right? And that will be the same. And the lack that we have is data for validation. And as soon as we are able to bring this data together in a way that it has all the semantics and so on that I was saying, all the data from these cyber physical systems, they transfer to a worldwide lab. They transfer that, each of these machines, each of that robot is producing data every day, and we can use it for validation of models in order to make our predictions better. And this is summarized in this infrastructure. It's looking a little bit complicated on the first view, I know it, but that is the world of production engineering. And this is also the structure how we are working together. What you can see basically are the three domains in the verticals of production engineering: the development, the manufacturing and production, and the use of the products. And if you look at the horizontals, then in the lower blue part, you can see this proprietary software that engineers in the different domains are working with. This data is proprietary. It is not exchangeable right now. It is maybe, for example, from CAD to CAM. But if we talk about, for example, connect data from the client with production data or design data, in my opinion, we are far away from that. So that's clearly what we want to do, and I explained to you this idea of the digital shadow, and this depicts it a little bit. The core of the research that we're doing is in this green marked area of this infrastructure. That means that we are developing a middleware, kind of a universal language translator. It's like a PDF format for this data if you want, so for exchange with semantics. And the development of these digital shadows for different kind of production domains. What we can do with this afterwards is, in my opinion, not only the optimization of the production processes and the domains itself, but if we look at the development of products nowadays, in my opinion, I think there is a lot of potential to be faster. I'm personally coming from an area of aero engines, from turbo machinery. I was working long time for a turbo machinery a company based in Britain, and you know that similar to the car manufacturing, of course, that is a certified product. That means that all different kind of steps need to be certified, and I'm aware of the fact that it cannot be the same like in software, but I think that we can do more steps to a highly iterative innovation if we just accept that we can have this data before. So in a sense that, for example, if the aerodynamic design demands a radius of the part because there were calculations about the flow, which is very, 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 very thin, and production cannot even produce it, and you need to start all that process from the beginning, it would have been better to have this information before. Right? And of course, at the end of the day, also the question of the performance of the part, or was this part over-engineered itself? Or did production produce it in a way how design wanted to have it? And do we really use it afterwards in the usage of a part? So that's, I think, the major point, that these data from usage, from production, and from development need to come together. And afterwards, I think that this can be really a milestone, that can be really a paradigm change for engineering and engineering processes itself. Thank you very much for your attention.